Okay, this is the second part of the Astronomy Unit 1 video review. The first video was over the ancient astronomers and their contributions. The second part, which will be this video obviously, is over the celestial movements of the Earth and the sky. So we'll start with the celestial sphere and what that is. Basically, the ancients thought that the stars and a lot of the things, not planets, but the Milky Way, for instance, were kind of painted on to like this glass-like sphere that was kind of orbited above the Earth or something like that, right? So, because they didn't notice that the stars in the background moved, and they just kind of thought that was the background. Well, they started identifying where different things were moving relative to these stars, including the sun and the moon and different planets. So they started naming these things, so they needed some frames of reference. Some of these frames of references were the celestial poles and the celestial equator. The celestial poles and the equator are very simple. It's where the north and south pole are on the planet currently, and it's just projected onto this sphere. So there's the north celestial pole, south celestial pole, and the celestial equator is the Earth's equator just kind of projected out into space and goes all the way around the sphere. So you measure using the sphere using latitude and longitude relative to the Earth's latitude and longitude. So anything above the equator is a positive number, as in an example here, positive 45. It can go all the way to positive 90, which is the zenith. And it's inverse for the southern hemisphere, negative in the southern hemisphere. Right ascension is longitude and direction, and it uses hours, minutes, and seconds, just like longitude on the planet Earth, and it's based off of 0 off the prime meridian. Local directions are typically found using azimuth and altitude. When I say local directions, astronomers who go out in the field and just plop a telescope down are going to use azimuth and altitude. It's just a lot simpler because their telescopes will have these kind of measurements on it. In fact, most stars and catalogs will have azimuth and altitude numbers for a given certain date. Azimuth are the cardinal directions on the horizon. So if you start here on the north, right, which was 0, it goes all the way around to 360 degrees, which is also north again, because it makes the complete circle. So east is 90, south is 180, west is 270, and then again north is 360. Altitude only goes from 0 to 90 because as you go up to 90 here, it won't go to 91, which would make that like an obtuse angle. You'll never have an obtuse altitude angle, because what you would have instead, if it were at 91, you would go to the opposite side of the azimuth and come up 89 instead of 91 from this side. So only can go to 90 here, can't go to 91. So you would have to move your whole telescope around this way and then come on up here to 89 degrees. This is just kind of evidence that constellations move during the year. This is the reason for the zodiac. The zodiac symbols are based off of when we would see them at night, based on the Earth's revolution around the sun. So in December, we're going to be looking out to this direction, and obviously March here, and so forth. So we notice different constellations because the Earth is moving. Celestial sphere makes it easy to identify certain astronomical events, I would say, such as the autumnal equinox or the vernal equinox, which is when the sun hits the Earth equal amounts of time, 12 hours on the northern and southern hemisphere, hence the equa. So also the summer solstice and the winter solstice can be seen in the celestial sphere because they follow this line right here, which is called the ecliptic. And the ecliptic is the supposed path of the sun around the Earth. Now, obviously, the sun doesn't go around the Earth, and we're quite aware of this now. But if you were to see the sun high in the horizon, then it is in the summer, and if it's low in the horizon, while it's still daylight, then it is in the winter. So it doesn't mean that the sun is going around the Earth. It really is an indication that the Earth is going around the sun at a tilted orbit like this. But that angle, that tilted orbit is 23.5 degrees. This is kind of reiterating what I was just saying. This shows that the sunlight hits the Earth at different angles based on that 23.5 degrees tilt that the Earth is. So here in the summer in the northern hemisphere, the sun is hitting more directly onto the northern hemisphere, therefore it's hotter, right? So the more direct light hits the surface, the more infrared energy is absorbed. Inversely, if you look at the winter the winter solstice, that light is being spread out over a greater area. And as that same amount of light is being spread out over a greater area, not as much energy is being absorbed by the planet. So therefore it's colder. So distance of the planet is from the sun has nothing to do with the seasons. It has to do with the angle in which the sunlight hits. So here on the equinoxes, right, the autumnal and the vernal, it's getting 12 and 12 equally. So it's a fairly similar temperature on the entire planet. Now, that's obviously within reason. You have the solar day and the sidereal day, or the sidereal. It's technically called sidereal, but it's easier for a lot of people to remember the sidereal. Solar day is the day relative to the sun. It's the day that you know of, 24-hour night and day cycle, due to the fact that the Earth rotates. The sidereal day comes from the word sidereus, which means star. It's the day relative to the stars. Now, what that means is that it's slightly different than the solar day. It's 23 hours and 56 minutes. And this is due to the fact that the Earth rotates and revolves, and it's 4 minutes shorter than the solar day, because as it's rotating and revolving, going two different directions, it's having to go one less degree every day to make that complete sunshot. So from here's A here and here's A here, right, dead on at noon, right, it doesn't have to go quite as far the next day to be full-on sunlight in the same position. Now, it's 4 minutes, it's not that big of a difference, I understand that, and most people understand this too. However, it is an important note to make, because it really just points to the fact that Earth not only rotates and sits there in one single spot, but it rotates and revolves. Speaking of that, rotation is the spinning of a body on its own axis, right? Like the Earth rotates, and it makes the day. That's another diagram about the sidereal day. That 4 minutes coming into account there. Revolution is one of the other movements that the Earth makes, and it is movement of a body around another body. The Earth revolves around the sun. The moon revolves around the Earth. So that's what's called the synodic month. And the synodic month is 29.5 days. That's how long it takes the moon to revolve around the Earth. So the Earth does both movements. Of course, it rotates around the sun, rotates around its own axis, then it revolves around the sun as well. Moon does that as well. This comes back to what I was talking about earlier, how the sun's supposed path, the ecliptic, makes the seasons different, right? More direct light here on the northern hemisphere makes for a warmer northern hemisphere, hence the summer. June 22nd, June 21st, these are the summer solstice. This is the summer solstice. This is the longest day of the year, because from that day on, as it starts going towards September, the sun won't rise as high in the sky, and it will therefore not shoot as directly onto the northern hemisphere. So it comes down to a certain point, and then it's still going to hit the northern hemisphere here. It's just now on the December 22nd, the winter solstice, the shortest day of the year. It will be spread out over more area, as that showed in that previous slide, and it therefore makes the energy not absorb as well, and the planet is colder in the northern hemisphere here. And obviously, inversely, it's more directly on the southern hemisphere, so it's summer in December in the southern hemisphere. Last movement that the planet does that's kind of not known to many people is the Earth precesses. It's called precession, and it spins like a top, wobbling slowly over time. And it is very, very slow movement. It takes about 26,000 years. That's slow for a human time scale. Obviously, astronomically, that's not that slow. So what this really does is it just kind of spins around. The North Pole kind of ends up pointing to other stars. So currently, the North Pole is, you can kind of see this here, how it's kind of wobbling around like a top. Currently, the star that is right above the North Pole is Polaris. Polaris is the North Star currently. It will not be the North Star for very long, relatively. And then you'll have these other stars like Vega will be close to the North Star in the year 14,000 AD. Thuban will be the North Star in the year 24,000 AD. It was also the North Star in 2000 BC. So it is just a very constant pattern that continuously moves. We just happen to have a star that is very, very close to the actual path currently, and that would be Polaris. It's not the brightest star in the sky. It's not very easy to find, honestly, because it's not that bright and it's not that discernible unless you just happen to have very good directional sense or a compass of something or something like that. So I believe that is it. All right, so that is celestial movements, which is part 2 of the Astronomy Unit 1 unit.